Okay. Are you ready? Now you should also have the textbook ready. We're using a new book now, right? We finished the entire volume 1. That's quite an achievement. Chapter 7. Starting from chapter 7, we are entering the realm of integration now. If the previous book is mainly focused on differentiation, and that is the end. After the application, that's the end. At school, I will still use a few lessons to practice with you. But with the extra lesson, I think we should carry on with the learning. Now, 7.1, the concept. Now, you can see this equation. This is the differentiation equation. F prime equal F. The two F's are different. In the past, I always say, oh, this is the derivative function. I think I always mention that. So you know this is the derivative function, this one. But on the left, I don't know if I mentioned that, the name before. We call this the primitive function. Okay, they are like the opposite of each other. This one is the primitive of the other one. And the derivative is the derivative of the primitive function. And also, this is, I think we all already know that ddx is a verb. That means to do something. Okay, and dy dx is a noun. That is the derivative function. One is to do differentiation. The other one is the outcome of the differentiation. And the process of finding the derivative function is called the differentiation. It means to cut things into pieces. I know you may think, oh, when do we cut things to pieces? It's abstract, like it's an abstract concept, because when you do differentiation, you are cutting this part of the curve and cutting it very small. Do you remember? Because we have to do the first derivative. Sorry, we have to do the first principle. And the first principle means, in the first principle, you need to cut this curve into very small pieces. So the name comes from, differentiation comes from to cut things into pieces. Anyway, that's the end now. We already finished it. Now today we need to learn what is the opposite operation of differentiation. That is to do it backwards. Now to do it backwards, you will see on the left, in the past, this on the left is the primitive, on the right hand side is derivative. Now to do it in the reverse way, you have to integrate. It's a new word, but anyway, you just bear with me. You have to do something to the derivative function and change it back to primitive function. Okay, so on the left, you see we need to do something. One moment. Now on the left, we need to do something. Now you will see this symbol. This looks like an elongated S, basically S dx. This is like ddx, but the opposite. That is to do something. This is a verb. to do something. And we put the derivative function inside. That means we need to do something to the derivative function. Now here we don't call it the derivative function, we call it the integrand. Integrand means I need to do something to this function. Now the outcome is this. This is the outcome. The outcome means we already found the primitive function. Now the outcome is this, the primitive function. But you will see that it's not entirely the same. It's not like, oh, the primitive function derivative equal to the derivative function. And then when you do it backwards, you're supposed to get the primitive function, right? That's called the reverse way. But you can see that apart from f, the primitive function, we also add another constant to it. Now, this is, I think it's very easy to understand because for different functions, sometimes their derivative functions are equal. For example, x squared derivative equal to x. X squared plus 1 derivative also equal to x. X squared plus 2 derivative also equal to x. So if you integrate 2x, you put 2x inside. Now, which primitive function are you going to get? It's unfair to get this one. It's unfair. You're supposed to get all of them. So that's why the outcome is one of the primitive function. Plus c. C here, c is a constant, because if you add a constant, it doesn't change the derivative. That's why when you integrate, you're not supposed to get one primitive. You're supposed to get one primitive plus any constant. Here we call it a constancy, an arbitrary constant, meaning it can be anything. It really does not matter. Okay. Now here, the outcome is a noun. This integrate f of x is a noun. This is the outcome. And it means the indefinite integral. Now here, the indefinite is added because we don't get a definite answer. What do I mean by definite? By definite, I mean, I get f, but I don't get f. I get f plus c. That makes it indefinite, meaning it's not just one answer. Indefinite means not sure if it's just one answer. Anyway, this whole thing is an integral. It's why do we call it integral? Is because it's the opposite of differentiation. The differentiation means to cut the graph into pieces. Now we need to put them all together. So that's why the naming of these concepts. Oh, why is it called integration? Why is this called the outcome is called an integral? Okay. Anyway, now the process of finding the integral, also you can say finding the primitive function of the derivative, is called indefinite integration. I hope that's clear. I'll give you one quick example. Can you rewrite the differentiation? This is an equation of differentiation into the form of integration. Okay, I think in your mind you just imagine, oh, this is just like a change of subject thing. Okay, now this is the derivative function, so I need to put the derivative function inside. Now here I need to write 4 inside. Put the integrate sign outside and then put the derivative inside. And the outcome is the primitive. The outcome is the primitive. But because it's indefinite, we need to add an arbitrary constant c. And then you're done. Okay. Now for the second one, again, you will write this first. You will write this first. And then you will put the derivative in. Okay. And then you will put the primitive on the right-hand side. But it's not just one primitive. It's all the primitive functions. So plus c. The last one. There. dx. And I put 2e2x and equal primitive e2x plus c. Okay, if you can do that, then we finish the first lesson. Let's go to the textbook and see what kind of exercise we can get. Now on page 5, if I show you, then it's already the answer. Maybe I show you anyway. I show you anyway. And then at least you can see. On page 5, this is this exercise, classwork. You see the differentiation, right? And you write the integration here. Okay. Now maybe I change it back. I don't know how to make the answer go away. Let me see. Now, if you have the book, can you practice now? Okay. Now, here I just I copied one differentiation from my notebook. Now maybe you can change this differentiation into integration. Now I'll ask one of you, so you can tell me how you would change it. Chen Hei, can you tell me what the answer is for this one? Chen Hei?
Is it 1 over?
How do you change it?
The integral of 1 over x and
Should just say
dx.
to integrate
Yes.
and then
Put the 1 over x inside.
you just say 1 over x dx.
Yes, and it's equal to ln 2x
Log
plus c. Log 2x
x.
plus c.
Okay. Okay, that's good. That's good. I hope that's easy. I hope that's easy. Anyway, that's the concept. That's the concept. If you go to the textbook, you can see it's just one page. Basically, you can see this tells this diagram shows you the relation between differentiation and indefinite integration. That's it. That's it. Let's look at the second part. Now, the second part of this chapter is to do basic integration. Now, we cannot, every time we cannot just, you are given and differentiation, you just rewrite it into differentiation. Sometimes you're not given most of the time you're not given the differentiation. You're just, you're supposed to find the integration yourself. And to do that, you need to do differentiation backwards. That is not easy. So we will give you a few basic formula. These are formulas, and teach you how to use them. The formulas are given to you in groups. It's not just one, because just like differentiation, one formula can only be applied to solve one kind of function. If you slightly change the function, you cannot apply that formula anymore in differentiation. Now, in integration, it's the same thing. For each kind of function, we have to integrate in different ways. That's why it's always like a lot of formulas, okay? Now, 7.1, basic formulas, okay? Now, when you look at them, you just need to, later on, you just need to know how to use them. But when I first introduce them to you, I would just prove them to you in a way to show you, oh, this is correct, okay? Now, for example, why is A correct? I'll just write in a marginal place. Now, A is correct. You can look at because kx prime equal k. Therefore, the integration is correct. Now, right now, you just follow this logic. Now, why is this formula correct? Because the differentiation formula is correct. Therefore, you write it backwards. Must be correct. Now, for the second one, why is this correct? Because xm plus 1, m plus 1 prime. The differentiation is m plus 1 xn m plus 1 equal xn. Now, because the differentiation is correct, so backwards, it's correct. To integrate xn dx, that is equal to xm plus 1, m plus 1 plus c. Now here, m must be a constant, okay? Moving on. C. Now, why is C correct? Now, why is C correct? Now, you can see that C has, it's not very easy for C, because in C, it has an abstract sign. But when we studied differentiation, we never differentiate anything with an abstract sign. Okay, so this one is not so easy to check. Not so easy to check. Now, I will show you. I'll show you. Now, why is C correct? Because to differentiate this function, I cannot just differentiate because I don't know the formula of this. I don't know the formula of this. I will divide this into two pieces. Now it's called a piecewise function. Now sometimes it's equal to this, sometimes it's equal to this. I will change it to it's equal to log x if x is bigger than 0. It's equal to log negative x when x is smaller than 0. I hope you agree with me. That is the meaning of abstract value. Here, abstract value means I will change it to the positive one. Now, if it's x itself is already positive, then I don't have to do anything. But if x is negative, I have to add a negative sign, so the outcome is positive. You know what I mean? Now here, negative x is a positive value, and that can only make sense when x is negative. That log inside log must be a positive value, and that is the outcome of the absolute value of x. Okay, now it's piecewise. Okay, that's piecewise. Now, okay. Wait. Now, Bailing just asked me a question. One moment. Now I need to differentiate. So I will differentiate this. I will differentiate this as well. Okay, I will differentiate piecewise. Now for this piece, we know it's equal to 1 over x. That is one formula we learned in differentiation for that one. For this second one, we know it's equal to 1 over negative x, and then chain rule, remember? And this is equal to 1 over negative x times negative 1. The outcome is also 1 over x. Okay, so although this function is piecewise, but in the end, no matter what x is, now x can be positive, x can be negative, but after differentiation, the outcome is 1 over x, no matter what. Okay, so you can say, oh, no matter what is 1 over x. Okay, and that is why C is correct. Now later on, I will show you how to use it. Is that okay? I'll show you. I'll show you. Bailing, let me look at your question. You asked me, Ms. Chen, can the formula be changed? I will answer you on Monday, okay? But anyway, right now you just use this formula C. Okay, if you can use it in the examples, you will use formula C if you can. Formula D, very similar. Now, why is this correct? Because the differentiation is correct. If you differentiate e to the power x, your outcome is e to the power x. That's why when you integrate e to the power x, your outcome is e to the power x as well. Part E, this one. Why is E correct? I have the last tiny space, but I think we can explain. Now, for this one, because 1 over k e kx prime is 1 over k e kx times kx prime. That is 1 over k e kx times k equal e to the power kx. Now, this is not a very simple differentiation. This differentiation, I have to take out the 1 over k. I have to differentiate e to the power u and du dx. It's a chain rule. It's not a simple differentiation. Anyway, afterwards, I will find out 1 over k and k cancel each other out, leaving me e to the power x only. That's why when you integrate e to the power k times x, you are not getting e to the power kx, you are getting e to the power kx divided by k, and that is the primitive function. Now, d and e, sometimes in some other textbooks, they won't teach you d and e separately because d is just k equal 1, a special case when k equal 1. But anyway, in our textbook, they are introduced to you separately because d is considered a very easy differentiation, where e is not so easy differentiation. So that's why when you integrate, you need to add a coefficient in front. Okay, enough said. Enough said. Let's apply. The first thing, you may ask me, oh, is there something missing? Why is there no function inside? Now, girls, sometimes you will see things like that. That means it's 1 inside. If it's 1 inside, I just don't write it. I know it's lazy, but that's what it is. People do that. It's 1 inside. If it's 1 inside, I will apply the first one. So the answer is 1x. 1x. So x and plus c. That's it. I apply formula A. Formula A. The second one, integrate x5 dx. For this one, I will apply formula B, but here n is equal 5. So I will do x5 plus 1, 5 plus 1, and then the answer is x6 divided by 6. Now, if you have any doubt of your own answer, you can differentiate quietly to check. This is to check, right? You can differentiate and see if the outcome is really x to the power 5. If it is, then you're correct. But you don't have to really do that. Once you practice enough, then I think you're okay. The next one, you're doing x to the power -7 dx. That's also formula B. But this time, n equal -7. Okay, like I said, you can leave your answer in negative index. You don't have to change it to fraction. Okay, you don't have to. In compulsory part, you will have to, but in M2, you don't have to. You can leave your answer like that. For part D, I also use formula B. But first, I will change it to power so I can use formula B. That's 4 over 3. And then x 4 over 3 plus 1 divided by 4 over 3 plus 1. Okay. Now this time, the fraction inside fraction is not allowed. So you must do 3 over 7, x 7 over 3. Now the fraction inside fraction must be changed to 1 fraction. And that is, I mean, the protocol. Okay, that's example 1. We will do example 2 before we do any exercise, okay? Now, example 2, this one, e2x dx, going to use formula E. So formula E, oh, no integration left. Formula E is 1 over k okay? 1 over k, e to the power kx, here k equal to. Okay? Part B. For this one, we don't have a formula yet because we don't deal with fractions. But anyway, you can change fraction to negative index. After doing that, you can use formula E. And then you're done. Last example. We don't deal with radical sign, so change radical sign to index. And then we use formula E. This time it's 1 over 2, e to the power x over 2. And the outcome is 2ex over 2 plus c. Again, if you're in doubt of any of the answers you get, you don't know if you're whether or not you're correct, you can differentiate and see if you get it back. If you get it back, then you're correct. Okay, let's do the exercise from the textbook then. Again, when I show you, it has the answer. But when you are done, just let me know. Quick practice on page 7. Let me know if you're done. Now this time I didn't print the classwork onto the notes, but I think there is enough space. You just write and then you quickly let me know. Let me know. Now, if you're done with these questions, you can go to next page. And maybe I show you the maybe I show you this and then you can see. Oh, you can't see. Page 7. This is page 8. On page 8, you can do this. On page 8, there are 3 more. 3 more.
Ai cao bảo vệ.
Okay. I don't know, but I think it should be done. It should be done. Now you may think, oh, maybe we haven't practiced we practice A, B, and E. Maybe not D. D is too easy. But we haven't practiced C yet. Later on you will. Later on you will. Anyway, let's move on to the next formula. Now, this is to say that in integration, just as differentiation, you don't have to really, I mean, you can take out the coefficient when needed. Now, this reason is because in differentiation, you can take out k, remember? You have k times f, but you can take out k. Therefore, in integration, you can also take out k. It should not matter. I mean, the k, you multiply first before integration or after integration, it should not matter. So that's why here, if you have -1 times f, and then it can equal negative integration f. You can take out -1. If you have a constant, maybe pi, maybe some other value, you can take it out as well. But pay attention that the thing that you take out must be a constant. You cannot take out x because x is a variable. Now, you can take out pi, but you cannot take out x. I hope you know the difference between this pi and x. It's not allowed because it's not. It's just not going to equal. Okay. Now, as to the addition and subtraction, it's also very easy because in differentiation, addition and subtraction are easy. You can do it separately. Then integration, you can also do it separately. Okay. However, anything else you cannot take out or do it separately. For example, you cannot take out sine because sine is a function you cannot take out. You cannot do this. You cannot integrate sine and change it to sine integrate. It's not going to be equal. I think in limit, you can do that. In limit is the sine of the limit is the limit of the sine. But in integration, you can't do that. And you cannot separate product because in differentiation, you can't. And quotient as well. They're not equal. Not equal. It's very easy to verify they're not equal. It's obviously not equal. But later on, you will, I think we will see it. When you make a mistake, you will see. Anyway, let's do more integration, using all the formulas. For this one, I will first take out 6. That's one formula used. Okay, and then I will use formula B. Okay, so it's like a combination, 2 steps. And then you simplify. Now, with this simplification, it's not easy. You can just use your calculator. Don't just don't do it by yourself. Okay. You see, I just used the calculator to find this. I just used the calculator to find this. Part B. Okay. Now for this one, I will take out -1/3 as a constant. Okay. And now I'm using formula C. Now, this is the first time we use formula C. Now to use formula C, you just remember to write log and don't forget the absolute value sign. Is that okay? That's to use formula C. If you integrate 1/x, you don't get log x. I know it's kind of, you're not used to that. You think because log x differentiation equal 1/x. Now, I know that some students would want the integration to equal log x, not log absolute value x. But what you didn't learn in differentiation is that, do you know that log -x differentiation is also 1/x? Now, if you know this is something we didn't learn. Sometimes we do practice, but we never learn this differentiation. But right now, you know, oh, this differentiation also exists. That's why when you integrate, you should get both. Now, to get both, that means log absolute value x. Now, if this bothers you, you should discuss with me until you feel comfortable. Okay, part C. E to the power -x divided by 5 ex dx. You take out 1/5. Now remember, the negative sign you cannot take out. This negative sign is not a coefficient you can take out. This negative sign is inside the index. It's not a constant. It's not a coefficient. So that has to stay. -x has to stay. And then you will use formula E. Okay, and then you're done. Okay. Now let's go to the textbook and do the exercise there. Example 3. Again, I show you the answer right away. There. Page 10. Page 10. Let me know when you are done. This time I really want, I need to see hands before I move on. Okay. I think almost finished. Example 4. It looks very scary, but it's not. I recommend copy the question. That is to integrate this. It means to integrate each one separately. I also take out the coefficient. Now, because this is addition, subtraction, so I'm separating all of them. I also take out the coefficient. And for the last one, I didn't write 1 dx. I just wrote integrate nothing. Nothing means 1. Nothing means 1. And then I'll use formula B. 3 x 2 plus 1, 2 plus 1. Now here I should write add C, but I won't. I will write add C at the end. So here 5 x negative 2 plus 1, negative 2 plus 1, plus, for the last one, I'll use formula A. And then plus C. Because plus C, plus C, plus C, if you plus C 3 times, that means 2 plus C. Now C is a constant that can be anything. So 1 C is enough. Okay, and then you simplify. And then you're done. Next one, copy the question. And then I'm separating. And when I'm separating, I'm also take out the coefficient. Also, I'm rewriting the fractions and the thirds into the index form. As a new learner, you probably should remember to write ds all the time. Otherwise, it's not complete. Do not just write the s. You need to write s dx, s dx. And then I'm going to use formula E. Okay. Huh? Sorry, this is not next. Sorry. Made a mistake. I made a mistake. Huh? Wait. It's e to the power. E to the power. Sorry. Can we change it to e to the power? It doesn't make sense if it's x. Can we change this to e to the power? E to the power. E. Otherwise, I don't know how to use it. E. We've never learned a integration that is x to the power x. It just like no, it's e to the power x. I was like, oh my. It's 1 over negative 3, 1 over k, e to the power negative 3x. That's the first one. Plus 5 over 2. This one is 1 over x. So you write log absolute value. Okay. And for the last one, formula B, negative 1 over 2 plus 1. And then x negative 1 over 2 plus 1 plus c. Formula B. So in the end, it's negative 2 e negative 3x plus 5 over 2 log absolute value x minus, now this is difficult, just use the calculator, okay? This is 4 x 1 over 2 plus c. Is that okay? I hope so. Just leave the absolute value there. Just leave it. The answer has absolute value, that's fine. At this stage, it's fine. Later on, we may have to do something, but at this stage, it's okay. Okay? Now let's do the exercise from the textbook. Here. Page 10. Page 10. Practice. If you can do it quickly, that's fine. Like I said, don't forget to write dx. And don't forget to write plus c. When you are done, let me know. Now with this integration, it's not about the speed. It's about the accuracy. It's not easy to get it correctly. Okay. Next. You're very fast. Example 5. Copy the question. Remember that you cannot separate product in the integral. You cannot. So what you can do is to expand. I will simplify. I first do expand and simplify, and then I will separate them. Remember to write dx. For the last one, I will take out 2. You can take out the coefficient, but you cannot take out this. That is not coefficient. You have to keep it. And then use formula E. Use formula A. Use formula E. Plus C. Simplify the answer. And then you're done. The answer, yes, that's it. I don't think you can do anything to the answer. Next one. Copy the question. Now, since we cannot separate product or quotient, you have to expand. So what you do is okay. And then you will write 4 terms separately, and each one is a power. Okay. And then you separate them. Take out the coefficient. Remember to write dx. Remember to write dx all the time. And then use the formula. Now this one is to use formula A. Formula A. The last one is to use formula C. Log x. And then you simplify. Okay. Now right now you have no way to simplify the absolute value, so you just have to leave it on. That's the answer. Classwork. 7.5. Let me know. Let me know. Okay. Example 6. Example 6. It's given a derivative. Can you find y? Now, if we follow the first lesson concept, now you need to tell what is what. What is what? Now, dy dx is the derivative. This is the derivative. Okay. Now we know this is derivative, but what is y? What is y? Now you can see y appear here, right? Y appear here. So on the left, you have d dxy, right? That means y is the primitive. I hope you understand what it means. So here y is the primitive function. So to find y means to find the primitive. Therefore, you have y equal integrate the derivative. Okay, and then you just integrate like this. E to the power negative 2x dx minus x to the power negative 2 dx. Okay, and then you will use different formula. For this one is formula E. For this one is formula B. Okay, and then it's 4. Actually, I need to multiply 4 inside. So 4 multiplied negative 2, that's negative 2. E negative 2x. And this one is plus 4. E to x to the power negative 1. Okay. And then you have 4 multiplied c. But you won't write 4c. You will just write c. I know it's not 4 multiplied c is not 4c, but since c is arbitrary, I don't have to write a more difficult c. It's just a constant. C here means any constant. So you don't write 4c, you just write c. Okay. Now, if you're concerned, you can write c outside at the beginning in the first place. You can write it outside in the first place. But anyway, even if you write it inside, the final answer should be just c. Okay. I hope that's clear. Now you do the exercise and I tell you something funny. By funny, I don't mean funny. You don't laugh. Exercise. This one. On page 12, you have this. This one has no x in it. It's t. How do you solve that? Let me know when you're done. Huh? So quickly. So quickly. Okay. Now for this one, I think I need to show you the answer because of the notation. Now this time, I think you know we need to change x to t, but not just in the derivative. I should also change the integral, this part. It's not dx anymore, it's dt. I hope you realize that. I think so, right? And then you expand, and then after expansion, you should remember dt, dt, dt. And in the end, plus c. I remember plus c, plus c. Now, that I think it's necessary to notice the formulas we have. Now, we give you the formulas in x. Now, obviously, you can change it to other variable. Now, when you change to other variable, you should notice that everything must change accordingly. For example, the first formula, you should be k dt equal kt plus c. Okay, if you want to change x to t, then everything, everything. Okay, now if that's correct, you should expect something else is wrong. For example, if I have this one, for example, if I change it to x and dt equal x m plus 1 m plus 1 plus c, and it obviously is wrong. If you change dt, if this is not dx, it's dt, then the formula is no longer correct. You know what I mean? But you will know, you will know later. Oh, right now you may think, oh, how should I make such a silly problem? It's possible. It's possible. Sometimes later on, when you deal with more variables in one question, then sometimes you may forget. You may forget. Anyway, so far, no problem. I was mentioning something funny is that I don't know if you are like me, because when I learned this, I doubt the weirdness of this symbol. You see, we don't say integration and just write integrate, like write I, like to integrate. Instead, we use this very weird thing like this. Like you must ask yourself, at least yourself, like why did we use this, right? This seems so weird. It's not it's not something that you write all the time, right? It doesn't feel very comfortable. It's not convenient. But somehow this is what we choose to represent, oh, we need to do integration now. But something is funny with this though. I hope that if I do it this way, then it can somehow reveal to you the notation, how this notation came to be used as we are using it now. Because in the past, there were debate over this, like how to write it. Anyway, this notation comes very, I mean, it was invented very naturally though. I don't know if later on you will slowly realize this thing, but right now I know if it feels weird. But anyway, for this question, now, if you allow me, now this is not, I know, normally teachers won't do that. Eh. Why do I say, I don't know. Now, normally teachers won't do that, but if you do that, if I allow you to do that, you will see that. Now, in the past, the dy dx was seen as a fraction before. So if I have dy dx equal 1 over e to the power 2x minus 1 over x. Anyway, the right-hand side does not matter. Now, in the past, I think it is allowed to write this. You can write dy equal 4 you can separate dy dx. Now, I know this dy dx is not a fraction, but it's a limit of a fraction. If you remember the first principle, it's delta y over delta x and send delta x to 0. But anyway, it was not a fraction, but right now, if you see it as a fraction, maybe it's not entirely equal. It's approximately equal, maybe approximately equal. And then you can do the integration. Here we see it as a sum. If you allow me to do this, you'll find, oh, what if I integrate and integrate on both sides? Do you know what I mean? Now I can do that. Now, if I do this, you will feel, oh, this symbol really feels very natural when you use it. Now, if I do integration on both sides, you will see that on the left, I will have y, because integrate dy is y. That's the first formula, formula A. Okay, and on the right hand side, you have this. To integrate this with respect to x. That's what it means. But you learn it very slowly. You learn it very slowly. Now, anyway, this one, even if you don't understand today, you will come to understand this more and more gradually. When you learn more integration, you will see the point of this. But so far, you just know, I mean, by today, you just know, oh, in order to get the original, not the original, the primitive function, you just need to integrate the derivative function, and that's it. That's it. As to the symbol, I try my best to make you like the symbol, to get used to it, but I don't think it works. For a few days, at least for a few weeks, you're going to feel very weird when you use it. The symbol itself is weird, but you just have to keep using it and make sense of it. In the end, you will understand. In the end, now let's do 5 minutes break, and we will come back and cover a little bit of 7.3. 5 minutes. 5 minutes. Hello. We're back. Before we move on to the next session, I think it's important that at least you have a look at this exercise before the next lesson. That if we were at school, I would ask you to finish the homework. I'll ask you to finish the homework, but now because we don't have time, we need to at least have a look at these questions. Conceptually, you should know that these problems can be solved using one of the formulas. Sometimes you may need to take out the coefficient before you use the formula. But anyway, they can be solved using one of the formula because it lies on, it's either a power or it's a exponential or it's, what else are they? I think it's just power and exponential, right? If it's an addition and you separate them, right? So conceptually, you should know that although we haven't done anything, but you are able to do it. You know what I mean? That's what if I ask you to do exercise, then you should do it very quickly. Have a look. Have a look. For example, for question 20, you're not supposed to separate the product. You're supposed to expand and then separate the sum. I mean the difference. Right? And for level 2 questions, I think it's just the difficult. It's not the difficulty level. It's the complexity. The power is a fraction, but anyway, it's still the same. Also, it has more expansion in it. Even with the 36, the very weird one, but if you realize that pi is just a value and theta is just x, it shouldn't be so hard. Now 37, 38, I think. Now have a look at this. This is what you should have done. At least be able to solve using the formulas we introduced, A, B, C, D, E, A, B, C, D, E. You're supposed to solve these. Okay, these are, if you learn this, then I think the world should recognize you as, oh, you know how to integrate. Okay. At least these functions, they are not simple functions, but you can integrate them. Okay, so it's a huge chunk of problems can be solved if you know if you just know the basic integration. You can solve a lot of problems. Now, before we I mean, later on you will learn the application of integration, but right now you just know, oh, I know how to integrate a lot of functions now. Okay, so right now we move on to the next part. Now this is when things get complicated. Now that is integration by substitution. This part is when integration gets really out of hand. Now when one, like, any of the formulas cannot be used. It can happen though. It can happen though. Anyway, now before I introduce to you this huge thing, it looks ridiculous. I don't know how to tell you this. So my plan is I will show you example of how to do it. And later on, we will come back to explain this huge formula. This is one of the formulas. This is to change integration to another integration. So it's doable later on. But before we explain, let me show you how to use it. Because using it, there are a lot of ways of using it. Some of the ways are not so difficult. So I want to show you first. The first application of the integration by substitution is this. Look here. Now, normally, if you have a polynomial, like in this case, it's a binomial, usually I'll ask you to expand. But what if the n is very high, then the expansion is very difficult? Then there is a way to integrate faster without expansion. And the trick is this. This is what we call integration by substitution. Now, let me highlight this part. Dx is changed to dAx plus b. That is a change of variable, if you may. Now, right now what you do is, it's like multiplication, and then you need to divide. Now, because here I multiply a, so I need to divide a. Okay, so you just remember, oh, because I multiply, then I need to divide. Now, as to the plus b, we need to realize, at least admit, that it shouldn't change the outcome, because in differentiation, addition or subtraction should not change the outcome. Basically, you are admitting that dx equal 1 over a dAx plus b. They are equal. Now, why are they equal? I don't want to explain in detail. Later on, we will explain it, but right now you just know, maybe this way. Maybe we know dx ax plus b equal a. So maybe this is easier that way. That means dAx plus b equal a times dx. Maybe that's, you just need to agree with me and move on. Not completely understand, that's okay, but you agree with me. We will multiply a and divide a, and we will add b without doing anything. We just add b. Later on, if I need to subtract, I will also subtract without doing any compensation, because there is no need. Okay. Now, after doing that, you will see me take out 1 over a, because that's a constant that's allowed. And then I will do an integration with u and du. Now, this time is u and du. This part is u, this is du. And I'm able to integrate using formula B. I'll show you. I'll show you, okay? Copy the question. And change it. Okay, change it. Now, right now, you cannot use formula B yet, because this is not x. This is u, but this is not du. You see? You can only do u 1 over 2 du. That's fine. But now it's u 1 over 2 dx. Not the same. Not the same variable. What you do is you multiply. You change this to d2x plus 1. That means you multiply 2, and then you need to divide 2. And divide 2, you divide outside, because you can take 2 outside. Okay? And then, now, as to plus 1, you don't do any composition. As I mentioned before. Plus 1, you just leave it. You just need to divide, multiply and divide. Okay? Right now, it becomes 1 over u du. And then you can integrate using formula B. This time it's 1 over 2 u to the power m plus 1, m plus 1. You know what I mean? And then plus c. I know it's bracket plus c, but like I said, just plus c in the end. So this is equal to 1 over 3, 2x plus 1, 3 over 2 plus c. And that's the end. Now, although I didn't use any of this, the theorem, and like it's a bunch of symbols and you may really understand, but in the end, I got the answer, you see. The technique is to change dx to 1 over 2 d2x plus 1. Okay? Now, if you are in doubt of the answer, I can do differentiation to show you it's correct. Although integration is new, but differentiation is not new, right? You can differentiate. You can see it really is oh, sorry, I lost something. Oh, there is a coefficient. Yes. And then I will now in the end, you see, cancel each other out. 2x plus 1, 1 over 2. Okay, at least I can check the outcome is correct. Is that fine? I'll show you another example. For part B, okay. Sorry, not this example. Wait, one moment. One moment. Not this example. The next example. Sorry, not example 7b. 7b, we cannot use the same thing, but in example 9, we can use the same thing. In example 9. Next page, example 9. With this integration, I'm doing copy 6, 3x plus 5 to the power 4 dx. So it's equal to 6, 3x plus 5 to the power negative 4 dx. Okay. Now what you do here is now you want to use the formula, but you can't because this is not the same base. So you need to do 6, but 1 over 3, 3x plus 5, negative 4, and change dx to d3x plus 5. Okay, that's a change of variable. That's a integration by substitution. Dx is changed to another variable, Okay. And then you can simplify this. 3x plus 5, negative 4, d3x plus 5. Okay, and then now you can use the formula. This is basically, you can use u to the power negative 4 du. Okay, think about this. And then use the formula, negative 4 plus 1. And then u is 3x plus 5, negative 4 plus 1. And then the answer. Negative 3 plus c. Okay. I know. Let's go back. Let's go back. Apart from this type, you can also do it in this way, like this one. You will do it like if you have 1 over ax plus b dx. In order to use formula C, you want to change dx to 1 over a ax plus b. Basically, you think like, oh, you're multiplying a and then you're dividing a. Okay, and then you can integrate. And then you use, in this case, you can use formula C, you know what I mean? In this case, this is equal to 1 over a log ax plus b plus c. Okay, the last example of the same kind is in this. It's e to the power u. This u is ax plus b. So e to the power u dx. We can't use formula E directly. So I will change dx to this and then integrate. So in the end, this is equal to 1 over a e to the power ax plus b plus c. Is that okay? Anyway, that's one, at least you know how to solve some problem if your variable is ax plus b, but the real variable is x. That's how you deal with the problem. That's how you deal with the problem. You just need to change it to another variable ax plus b. Now, right now, if you allow me to explain this whole chunk of things, this formula, you can see that the very beginning of this formula is one integral and everything is in x. Okay. Now, the very end of this formula, everything is in u. Do you see? Now, if you don't look at the middle, then it's not so confusing because the purpose is to change one variable to another variable. Okay, but it's not so easy as the change of variable in other algebra. It's not so easy. You can't just change. That's it. You can't just change. You must realize that there is something that you can change to du entirely. And dx and du are not like, not so easy. The relation is not so easy. So what is the relation between x and u? You will see this as the normal, what I call a normal relation between u and x. But you will get, because you don't just change u to x to u, you need to change dx to du as well. So you can see that here you have, here these x are easy to change to u, but you need to change dx to du. So what you see is, in the function, you will have this is equal to du. Now, it's not so direct. It's this equal to dg, and dg is equal to du. But you don't have, I mean, essentially, they are the same. You want to change dx to du, but dx is not equal to du. It's g prime x times x equal du. Now this I don't know how to explain it to you now, but because u equal, okay, u equal g of x, therefore du dx equal g prime x, therefore du equal g prime x dx. So that is why you can see me replace g prime x with du. So in the end, everything is in u, but it's not easy to find g prime in the function. I will show you. Now, with this knowledge in your mind, you must say, oh, I must find the, you will see it. Now, here. Now, normally I would, with this integration, I have to expand this binomial. But I don't want to do that. I can, but I don't want to do that. It's too many terms. Anyway, there is an easy way to integrate if you change variable. Now, how do I do that? It's not so easy as the previous example, because in the previous example, you just multiply a and divide a, that's it. Because you only need to do a constant adjustment. You just adjust one thing, that is just multiply a, divide a. But here you can't, because it's not just a constant difference. It's a lot different. Because here in this question, I'm going to have a new variable. Let u be x squared. That's a new variable, you see? Now, right now it's integration in x. Look closely. See how I change x to u, okay? Now, because du equal x square, therefore du dx equal 2x, that's the differentiation, okay? And then I will change du to 2x dx. Is that okay? However, now this formula will provide me enough to change my integral. Now my integral is x1 minus x squared 8 dx. This is my integral. I have to change a whole thing back to u. How do I do that? Watch carefully. First, I will put this first, put this chunk first, and then I'll write x dx together. X dx together. But that's not the end, because I don't just need x dx, I need 2x dx. Do you see here? I need 2x dx. So here I will do this. I know it's a lot to do, but you bear with me. I will change this to 2x dx. But because I multiply 2, I will divide 2. Okay, that's my preparation. I need to prepare this so much so I can move on to my next stage. My next stage is to replace x with u. Then when I do this, I will do it everywhere. The first thing I do is 1 over 2, 1 minus u8. because u equal x squared, that's an easy substitution because that's just normal. I've done it before. But the new substitution is 2x dx equal du. This part is du. You see? So in order to integrate this function, I have to do a lot. I have to do a lot. I have to find, like, decide my new variable. Let's say, oh, in this case, it's x squared. In this case, it's an x squared. It's decided by me. I have to decide. And then I have to find a way to replace x with u at the same time, dx with du. And that replacement is not easy, especially with dx with du. Like I said, dx is not equal to du. It's equal to a function times du, you know what I mean? And the function has to be like so carefully placed so it can be replaced entirely like this. Now it's replaced. Now after it's replaced, then I can solve it. Do you know how to solve it? In this case, I will change it to 1 minus u8 d1 minus u. And because here I multiply a -1, I will add a -1 in front. Okay, and then it's equal to, this is something to the power a d something. It's a t to the power s dt. So it's -1/2, 1 minus u to the power 9 divided by 9 plus c. And then it's -1/18, 1 minus u to the, maybe not u, I change it back to x. And then you're done. Okay. Now, basically, all I want to say is that's not easy to do. And also, you must know that this is not the only variable I can use. If we have time, if we have longer time, I will show you that. I mean, next time, I will show you that this is not the only workable substitution. You can actually use some other substitution and also achieve the same result. So it is hard, but not entirely so hard. But anyway, that's what it is. With integration, why is it so difficult? Because of this arrangement is not easy to make. It's not easy to make this happen. I'll show you another example. Fine. Okay. Example 8. Now this, I don't know. I don't know what will happen. I don't know, but you have to bear with me. Now I want to, in the end, I don't know what will happen, but I want to replace u with maybe square root x plus 2. Can I do that? Bear with me. I'm thinking which way is easier. Which way is easier? Oh, this one is with 2 different substitutions. I guess we have to use this one then. Right? We have to. This is one of my substitutions then. 2 different substitutions. This is one of them. Now with this, I will realize that u squared equal x minus x plus 2 and x equal u squared minus 2. Just bear with me. Bear with me. So the whole thing is dx du equal 2u and dx equal 2u du. That's one of my substitution anyway. That's one of my substitution. Now I'm going to arrange my integral now. Now it's x plus 2 dx correct? I think so. Okay, I think so. So this one is x changed to u squared minus 2. That's the first change. The second change is this one changed to u. I think, follow me. This is x. This is u. Okay. It's the final one that's difficult. The final one is dx, and dx is 2u du. Oh, that's not difficult. Now this time is not so difficult. This time is not so difficult. It's not every time. Maybe because my choice of the substitution is easy. It's not always easy. It's not always easy. But this time, you see, I changed dx to 2u du again. Now, let me highlight. So everything is in u now, then I can integrate. This is 2u4 minus u squared du. And that is 2 times u5 over 5 minus u3 over 3 plus c. And that is 2 over 5 u to the power 5 minus 2 over 3 u to the power 3. That's one of the substitution. Anyway, we will repeat this definitely. Now you will do some exercise on the previous 2 lessons. That's all. That's all. I think next time we'll do better. We'll do better. Just think about the last part. Practice the previous exercise, and then think about what will happen next week. Okay, I'll see you. Bye-bye.
I'm sorry, Ms. Chen. For example 8, may I know whether should it be 2u squared instead of u squared? Like when we times 2 to u and
Isn't 2 taken out? Or 2u squared? Oh, sorry.
Thank you.
2u squared, yes. I forgot. Yes. 2, 4.
Okay, thank you, Ms. Chen.
Okay.